So in this video, we are going to look into series RLC circuit and we are going to analyze it by means of time domain analysis techniques. So specifically, we are given with the DC voltage source that is X of t, which is over here. And then we have an inductor of 1 ohm, resistor of 3 ohm, capacitor of 1 by 2 farad, and we are interested in the output response, which is in terms of the loop current Y of t. The input that we are given with is X of t, which is equivalent to 10e minus 3t u of t. Moreover, the initial conditions are y of 0 minus equal to 0 and y derivative of 0 minus is equal to minus 5. So in this video, we would be calculating the output response, that is y of t, 0 input response y naught of t, and a 0 state response, that is ys of t. Let us first state that we can simplify the initial conditions even before starting. So in the absence of any impulsive voltage, the loop current would not change instantaneously. So this would mean that y of 0 minus is equal to y of 0. So this is simply 0. And similarly, y dot of 0 minus is simply y dot of 0, and this is equal to minus 5. So just a small translation at the offset. So we know that the output response of the loop current y of t is an addition of the 0 input response and a 0 state response. So this is simply zero input response, transient response, or a homogeneous solution to a differential equation. And similarly, ys of t is 0 state response, steady state response, or we can also call it as a particular solution of a differential equation. So in our prior videos of linear time invariant systems, we were not having any initial conditions. So in that case, the ys of t, so this was actually equivalent to x of t convolved with the impulse response h of t. That is in the absence of initial conditions. But since now we have these initial conditions, so the 0 state response would be added with the 0 input response y naught of t. So let us find y naught of t, and then from here we would build an intuition of finding the impulse response h of t, which would then be convolved with x of t to find the state response, and finally we'll add this with this to find the overall solution. Now using KVL and plugging in the values of L, R and C for this circuit, so we would have now differentiating both sides. So we have a second order differential equation. For later reference, let us call this as our expression 1. Now as a first step, let us move towards the 0 input response. So from 1, if the input is 0, that is x of t is set to 0, so the right hand side would simply be 0. So we have the second differential y naught of t plus 3 . So we can express this in a polynomial form, and we can say that d by dt is, say, s. So we would have y naught of t s square plus 3s plus 2 equal to 0. And the characteristic roots of this equation are simply s plus 1, s plus 2, y naught of t equal to 0. So the solution of zero input response would be of the form y naught of t c1 e minus t, which is coming from here from the first characteristic root, plus c2 e minus 2t. So say this is our second expression. But right now we have two constant coefficients, that is c1 and c2, that we need to find out using these initial conditions. So let us take one more derivative of the zero state response. So we would have y dot of t. So this would be simply minus c1 e minus t minus 2 e2 e minus 2t. So this is our third expression. Now from the initial conditions, y naught of 0 is equal to 0 and y naught of 0, the derivative of it is simply minus 5. So plugging this in the above two expressions, we would have 0 and this would be c1 plus c2, and then we have minus 5 minus c1 minus 2c2, and from here we can find the coefficients. So it's easy to find c2 first. So c2 is simply, if we just add, so c2 would simply be 5, and from here c1 would be minus 5. So hence the zero input response is simply y naught of t, and plugging in the values of c1 and c2 in 1, so we have minus 5e minus t plus 5e minus 2t. Say this is our fourth expression. So note that in this circuit, what we mean by zero input response is we are basically setting x of t equal to 0. So this means that for the circuit, we are simply shorting it and hence cancelling this root. So this means that x of t is equal to 0. That is, there is no potential drop across these two terminals. Now let us move towards the second part, that is zero state response. That is ys of t, and I mentioned that this is simply the input x of t convolved with the impulse response h of t. Note that this is one method of finding the zero state response. You may also look into the classical method of finding the particular solution of a differential equation to find the zero state response. But let us move towards finding the impulse response. Now from this expression, the order of the differential of the output, that is y of t, is more than the order of the differential of the input, that is x of t. Then there is a very simple form of finding the impulse response. So over here we can observe that the output has a second differential, whereas the input has the first differential. So it qualifies our criteria for a specific formulation that I'm going to present next. So under this condition, the impulse response h of t has a very simple formulation, and that is we need y naught of t, that is the zero input response, and we are multiplying it with whatever is before x of t, right? So presently we have d by dt. So if there was a 2 over here, that is 2 d by dt, so we would be multiplying 2 d by dt. Presently we have a 1 over here, so we are just multiplying by d by dt. So we have d by dt y naught of t and then we are multiplying it with the unit step function u of t. A very important point to note over here is that we are considering zero state response. That is, the initial conditions are not playing any role, right? So these would not be included in this expression, right? So we would need a standard formulation where we have not inserted the initial conditions. So this simplistic expression of the impulse response defines its own initial conditions, that is y0 of 0 is simply 0, and the first derivative is set to 1, that is y naught of 0, the first derivative of it is set to 1. So if it was a higher order differential, the last value would be set to 1. So hence setting y naught of 0 and y naught of 0, the derivative, in 2 and 3. So we would simply have 0 equal to c1 plus c2 and 1 equal to minus c1 minus 2 c2, right from here. So these two would conclude that c2 is minus 1 and eventually c1 would be plus 1. So for this, that is d by dt y naught of t, which is expressed over here. So if we plug in the values of c1 and c2, so we would have minus c1 e minus t. So c1 is 1, so we have minus e minus t, and then we have minus, so minus 2 c2, but c2 is again minus 1, so it will become plus 2 e minus 2t. So we have plus 2e minus 2t u of t. So hence we have found the impulse response, and next we are going to convolve it with the input x of t. So hence we have ys of t, so this is equivalent to x of t h of t. So note that x of t is equal to 10e minus 3t u of t. This convolve with the input, so that is 10e minus 3t u of t convolve with minus e minus t u of t plus this convolve with this one, so that is 10e minus 3t u of t 2e minus 2t u of t. So let us say this is ys a of t, and similarly this is ys b of t. So let us next calculate ys a of t. So if we need to convolve these two functions, that is, we have one function which is 10e minus 3. Let me change the variable from t to tau. So we have tau u of tau, and then we're going to flip this part. So we would have, note that we can bring this minus outside, so it will make it simple. That is, we can have a minus here and plus here. So in that case, so this is our 0. So we have e minus t minus tau u of tau, where this is t. So hence if we are sweeping this from left to right, so whenever t is less than 0, right, before this point, so these two will multiply and the area would be 0. But when t is beyond 0, right, so this and this would multiply. that is starting from 0 up to the point of t when it is moving towards the right side. So we have t, and then these two functions, that is 10e minus 3 tau times e minus t minus tau d tau. The unit step functions are already subsumed in the integration. 10 and this t are not a part of this integration, so they can be taken out. So we had a minus sign here, so we are going to multiply a minus here. So next, if we're taking this integration, so we would have 5e minus t e minus 2t minus 1. So we have minus 5e minus t plus 5e minus 3t. So that was the solution of first part, and in similar way we can solve the second one, almost similar approach, and this is going to give us 20e minus 2t minus 20e minus 3t. So as ys of t is simply minus 5e minus t plus 20e minus 2t and minus 15e minus 3t. So this is our zero state response. So now we have a zero input response, which is expressed over here, and then a zero state response. So again, the total response would be an addition of these two. That is, we have minus 5e minus t plus 5e minus 2t plus, for the zero state response, minus 5e minus t plus 20e minus 2t. So in this Matlab code, I have written the zero state response, which is over here, and the zero input response, which is over here, right? And finally, the total response is the addition of these two. So note that this code is also available in the description of this video. So let us plot this function. So in the plot, this is expressed over here, that is our zero input response. This is expressed over here, that is our zero state response, and the addition of these two is our total response, that is indicated by the red plot. So besides the zero input response and the zero state response, we have also another terminology which is called the natural response and the forced response. So that is y of t can be expressed in terms of natural response plus forced response of a system. So note that we have characteristic modes in terms of e minus t and e minus 2t. But these modes are also appearing in the zero state response. So if we combine this and this together, so that would become our natural response to a particular system. So in our example, this is simply minus 10e minus t plus 25e minus 2t. So this is our natural response for the series RLC circuit. And then the forced response is simply minus 15e minus 3t, which is the non-characteristic mode. So hence in this video, we started with the series RLC circuit for a given precondition or initial conditions, and we analyzed it by means of time domain analysis techniques.